Hello, Mr. Colati here. Now that we're experts at solving trig equations, we're actually going to look at trig functions. That is, y equals sine x, y equals cos x, y equals tan x. We're going to start by graphing these functions. So one way to think about this is to start by just taking, imagine taking every degree in the circle, so from 0 to 360, or in radians if you like. And for each of those angles, I'm going to find out what sine is, what cos is, what tan is. So I can type that into my calculator and I can fill in this table. So you can imagine I have, for every angle, I have all the trig ratios, all the values for y equals sine theta. Now I'm going to plot those, and I get this curve. This is a sine wave, or it's a sine function, see y equals sine x. It's sinusoidal, meaning it goes up and down like that. And it's periodic, meaning it repeats over and over again. That's one of the qualities we're going to find of all of these trig functions. If I do the same with cos, I get the y equals cos graph. Similar to the sine graph, it's been translated to the left by 90 degrees. So you can see that this the sine starts at 0 and goes up and down and back to 0. The cos starts at 1 and dips down to -1 and comes back up. And then over here we have something that looks very different, y equals tan x. Tan's a little bit different because there's an asymptote that occurs at 90 degrees. You can't have tan 90. Type that into your calculator. You're going to get it does not exist. If you notice, the sine graph repeats itself over 360 degrees. So does cos. Tan actually repeats itself every 180 degrees. So it goes up, asymptote, then returns to 0 by 180. Another way of looking at it goes from -90 to +90. It goes from this asymptote to this asymptote. So there are all the points, and that's how they map. And you should get used to drawing these. One trick I use to drawing these graphs is to kind of look at 5 key points. And I'm going to highlight those 5 useful points. The first one is an angle of 0, an angle of 90 degrees, an angle of 180 degrees, an angle of 270 degrees, and then technically an angle of 360, although this one's the same as 0. Right? These are 5 useful points for graphing. Oh, there it is, sorry. So a lot of these you'll get used to kind of memorizing these 5 points. I mean, sine goes from 0 to 1 to 0 to -1 to 0. If you can plot those points, you can plot the graph, you can draw that you'll get better practice at drawing that periodic curve. Cosine starts at 1, so it's a little bit starts a little bit further along. 1 goes down to 0, then -1 back up to 0 and 1. Tangent starts at 0, does not exist at 90. Then at 180 has returned to 0, right? So we have that kind of curve. Okay, so like we said, all of these functions are periodic, meaning that they repeat over and over again. There are lots of other periodic functions. You can imagine I could have a triangle wave going up and down, up and down. Anything that repeats over and over again is periodic. But these are the ones we look at in this course. There are other periodic functions related to trig, like the reciprocal trig functions, cosecant, secant, and cotangent, but those are not in IBSL. So remember, those aren't, even though you've been introduced to those in other math courses, they're not in this course. A little bit more about periodic functions, well, about sinusoidal functions. Anytime you have a curve like this, again, let me draw the cosine, you're going to get kind of good practice at drawing this graph. Oof, that's not my best though. We have a few things to define. So the first is the period. The period is how long it takes for one cycle to elapse. So that is the period. That's the x, the length of the curve, or how long it takes to go from start to repeat. Okay, actually we should talk about the 2 curves we just looked at. So the period for a sine wave, then, it takes 360 degrees or 2 pi radians to do one period to get to the point where you're going to repeat the curve. Same with cosine, 360 degrees, and we already talked about this. For tan, -90 to +90, it takes 180 degrees. So we'll just make a note about that. For sine x and cos x, the period is 2 pi or 360 degrees. For tan x, the period is pi rads or 180 degrees. Okay, the amplitude. This is the distance from the horizontal. So if this is my horizontal axis, it's kind of like the center point of the graph or the middle point of the graph, then this is my amplitude, the distance from that horizontal to the highest point. To calculate the amplitude, well, we can add up the highest point, the max point, and the min point, and we can, we can subtract the max and the min and divide by 2, and we'll find the amplitude. Oh, I didn't write this out. This is the distance from the horizontal axis to the max or the min. So A is equal to y max, y minus y min divided by 2. And it's always positive. And amplitude you can think of as how much the curve's been stretched. The horizontal axis is that central axis of the graph. It's like the middle point. The horizontal axis can be calculated by taking the max, adding it to the min, and dividing it by 2. I always think of the horizontal axis as the average, right? It's, even though I'm going up and down, up and down, up, this is the average value. So you're adding the two, max and min, and you divide by 2. Whereas the amplitude is kind of the amount I went up, so that's why it's a subtraction. Okay, those are some definitions. Let's turn to the page and talk about some transformations. And this page probably looks familiar because it's almost identical to one of our first, actually the first lesson we did, where we looked at transformations of all your favorite functions. So now we're going to return to it, which is a nice little review, but we're going to talk about transformations in terms of these sinusoidal waves. So let's start by looking at translation, which means that something's been moved side to side or up and down. We also use the word shift. So if I start with a sine curve like this, so this is y is equal to sine x, and I want to do a vertical translation, I add a number or subtract a number outside of the bracket. You remember kind of that terminology. So for example, if I add a value like d, this whole curve is going to move up. So this is y equals sine x plus d. The d is outside of the bracket. Remember I said back when we did this lesson so long ago, anything that's outside the bracket tends to impact the up or down, whereas anything that's inside the bracket tends to impact the side to side. Case in point, oh, and there's d there, right? So this is d. Okay, and negative is going to subtract. Okay, let's do this exact same thing, but if I have the sine curve, and this time I'm going to add or subtract a number inside the bracket, this is going to move me side to side. But remember, everything inside the bracket is kind of reversed. So a plus c, you would think that that's going to move you in the positive direction to the right. It doesn't. It actually moves you to the left. Similarly, a negative, instead of moving to the left, it actually moves you to the right. So there I've moved to the right by c. So this curve is y is equal to sine x minus c. And the original function is y is equal to sine x. That's a horizontal translation. However, we also call it phase shift. That's a term we only use when we're talking about periodic functions, trig functions, the phase shift of c units. So there's a little star there, you know, we kind of talked about this before. They're reversed, right? Right, the positive means left, the negative means right. Okay, let's go to our second type of transformations, which are the reflections. So in this case, I have a sine wave. Oh, sorry, there's one thing I always forget to write. I put that up as a note up here. But just note that IB writes two translations as like A and B. Whenever you see that and it's like, oh my god, what does that mean? Well, these two translations, this is just two translations. So this is the X translation and this is the Y translation, or this is the vertical. Sorry, this is the horizontal and this is the vertical. So if you ever see two kind of stacked like that, it almost looks like a vector. That's just telling you the two transformations you have to do. Whew, okay, let's go back to this. So we were talking about reflections. So there's y equals sine x. Now I have a negative in front. Remember, the negative outside the bracket tends to mean something up and down. So in this case, it's a reflection about the x-axis. And there's the x-axis there. So if I mirror it around that x-axis, it actually flips vertically, or kind of up and down. So this peak now becomes a valley down here, and I get this up here. So that's negative sine x. The alternative there is y is equal to negative x. So if I draw my sine wave like this is y is equal to sine x. Well, this is a negative, is inside the bracket. So I always think of that as a side-to-side thing. So it's like this whole function has been reflected about the y-axis and is now over here. It just kind of gets cut off, right? But it's periodic function, so it actually continues, right? Like it technically goes on forever. These graphs, just unless there's a kind of the interval's defined. So you actually see both reflections give you the same reflection, in this case, for the sine function. So this is y is equal to sine negative x. Okay, continuing now with the stretches. Now the stretches are where things can get confusing. Let's start with the vertical stretch. So I have my sine function, y is equal to sine x. If I have a number multiplied by my sine function, and remember that number's outside of the function, I would say in quotations, then that's going to stretch my graph vertically by that amount. So what's neat here is it's kind of logical. If you have a big number, then you have a bigger stretch, it becomes larger. So if I multiplied by say 2 or something, it's going to be stretched like this. Oh, hopefully you draw a better one than me. So this is y is equal to say 2 sine x. I don't want to overwhelm this picture. It could get confusing. But if you choose a number that's less than 1, so it's a fraction, like half, then you're actually not stretching it at all. You're compressing it by half. So it's going to become smaller. The amplitude is going to become smaller. When we do this in the horizontal, we do a horizontal stretch, it's the reverse, right? It's the same idea, but it's the reverse. So there's my sine wave, and I'm going to stretch by this factor. There's a factor multiplied inside the bracket, but it's the opposite. So if I have a large number like say sine 2x, instead of stretching, that's doing the opposite. It's compressing in half. So now instead of the function having a period that's this long, the period's half. So it ends here. So I have to do the exact same thing, but in kind of less time. So this is y is equal to sine 2x. So similarly to before, you see that there's a reversal here. A big number means that you're compressed. A larger number means that a big number means that you're compressed. A larger number means that you're stretched. The way that you're going to find you can tackle this one, because this tends to be the hardest one, is to think about how the period changes. So the period changes based on the b value. For sine and cos, the period is 2 pi divided by b, or 360 degrees divided by b. So for example, in this question, the b value, the number in front of x, was 2. So I took my original period of 2 pi, divided it in half, so I got half the period, it's just pi. Or 360 divided by 2 is 180. And so now my new period is 180, and I can draw the curve. For tangent, remember tangent has a smaller period. The period is going to be pi by b, or 180 degrees by b. So you're going to find that actually these stretches, horizontal stretches, are not so bad for the trig functions, because you're just going to change the period. Okay, let's turn the page and do some examples. Actually, let's bring it all together first. All of these transformations combine into this kind of master equation. Y is equal to a sine b x minus c plus d. So again, let's go through what all of these are. So the first one is a vertical stretch. How do I remember that? Well, it's being multiplied and it's outside of the bracket, so I know it's vertical. This is being multiplied inside the bracket. It's being multiplied, so this is the horizontal stretch. This is being added or subtracted inside the bracket, so this is the horizontal shift, or the phase shift. And then this is last, this is my vertical shift. And note that the negative here reminds us that it's reversed, right? The negative is to the right, positive is to the left. Okay, now in IB, we expect you in IB and an IB exam that you always do multiple transformations step by step. Don't try to do any kind of funny business where you're using 5 points and transforming the points and then doing it all in one go. You want to do step by step. And I would recommend to do your transformations from left to right. I mean, I would recommend to do the stretches first, but the easy way to remember that is just go from left to right. So for example, let's look at this function here. Graph the function y equals 3 sine 2x plus pi by 6 minus 1. Oof, wow. Look at how scary that equation is. But really, we can do this one step at a time. Let's look at all the different values here. First of all, we note that it's in rads. My first value is a is equal to 3, so that's my amplitude. Why don't we graph this step by step? So first of all, this is probably 1, 2, 3, and this is -1, -2, -3. It is a, I should draw it in rads. It is a sine, so let me start by doing the sine wave. Remember, this is the halfway point, so this is going to be 0, this is 0, and this is 0. This goes up to 1 here, and it goes down to -1 here. So once I've put those 5 kind of key points, which you should memorize, then it's just a matter of drawing the curve as best I can. There we go. So there's my first iteration. That's I'm going to write this really small, but y is equal to sine x, because there's lots to come. Okay, so let's look at my first transformation. We'll start from left to right. Y is equal, or so the amplitude is 3. So that tells me I have a vertical stretch by 3. So I'm going to take this graph and I'm going to stretch it by 3. That's not too bad. I'll write this in a different color. Vertical stretch by 3. So now, 0 doesn't change, it's still 0. This, instead of becoming 1, it goes up to 3, 0, -3, 0. So I get, it's much more stretched. There we go. And I guess I should label this one too. Y is equal to 3 sine x. Okay, so far so good. My next point, or my next number is, okay, this the value that's being multiplied by x, this is b is equal to 2. This is the one that can be confusing, right? This tells me that I have a horizontal stretch. Well, technically it's not a stretch, it's the opposite, right? If it was here, a big number means a stretch. Here, a big number means a compression by half. But it's easier to think the period is equal to 2 pi, right? I take my period, divide it by the v value, which is 2, so I just get a period of pi. I think that's easier for questions like this. So now, instead of this whole thing happening over the course of 2 pi, it actually happens up to pi. So now everything is kind of compressed and happens faster. So this is 0, this is up here, positive 3, negative 3. So I'm going to draw this sketch. And that one is y is equal to 3 sine 2x. Okay, so far so good. Now, my next step, now it should be easy, right? Because now I'm just doing my translations. The hard part's out of the way. C is equal to, in this case, pi by 6. But remember, it's the opposite. It's negative pi by 6. So that's telling me, let me get a different color pen, that I'm going to shift, horizontal shift. Again, you might get confused by negatives. I don't really care how you write it out, as long as you know that this doesn't mean to the right, it means left by pi over 6. Okay, so where is pi by 6? Well, this is pi by 2. So this is pi by 4 if I want to divide into quarters, right? This is this is 2 quarters. So this would be 1 quarter. If I want 1/6, it's actually less than that. So it'd be somewhere, it's not a great scale, but it'd be somewhere there. So I'd move almost a full point over. 1/6. 2/6 is third. Probably closer to here actually, before the halfway point. Okay, and then similarly, all these points are going to move over a little bit as well. So now I have there we go. I think I got that one. So that's y is equal to 3 sine 2x plus pi by 6. Okay, and the last step is to, I need another color. I'm low on colors here. I guess I'll use this highlighter. This is d of -1. That's a vertical shift down. So that should be straightforward. I take all of those 5 kind of important points, and then I just shift them down 5, and then I very carefully draw my graph. There it is. Perfect. And through a series of step-by-step transformations, I'm able to draw this kind of what looks like a very intimidating graph. Perfect. I think that's it. Okay. That does take a while. It's very rare you'll see a question in IB where you have to do 4 transformations. That's possible. This is kind of a better example of what you might see on an exam because it's very quick. You can test someone's knowledge with this question. Find the m and the n value given that the graph of the function y is equal to m sine x plus n. Okay, so we have to look at this. So what is m? Well, m is the number in front of sine. So m is a vertical stretch. And n is a vertical shift, right? So really what this is saying is, okay, you just have to figure out these 2 values. Though, how has this been stretched? Well, usually sine, okay, so the sine wave looks like that. Sine usually goes up 1, but here I find that sine goes up 1. From the horizontal, it goes up 2. So therefore, it's been stretched by 2. And what about the shift? Well, usually sine starts at 0, but here it's been moved down 3. So this has been it's been a vertical shift down 3, so n is equal to -3. So therefore, y is equal to 2 sine x minus 3. Actually, what you should write is m is equal to 2, n is equal to -3. All right, so that's that. And I know you've probably done this before, so a lot of this is review and hopefully shouldn't take too long. What might be new for you is the fact that we really need to be comfortable with the radian measure. So you should be really emphasizing the radian practice. There's lots of homework for this. Page 482, number 1, 2, 5, and 6. Again, trying to highlight the radian questions. And then we have page 478, number 3 and 11, and 474, number 3, 8, and 11. And I highlighted those because that is tan practice. It's unlikely, I don't think you've done as much tan practice. So there is lots of extra work there if you need more practice, but these are the questions I think you should do to refamiliarize yourself with the concept, get comfortable with radians, and get comfortable with the tan. Good luck with that, and we'll see you next time.